Let's do an example of the conservation momentum from my research area. So here we have a jet engine, and the flow is going to go in from the left here and out from the right, and the job of a jet engine is to speed up the air. So velocity 2 is bigger than velocity 1. We are going to simplify the problem by assuming that we get uniform flow, which means there's no change in velocity over the area here. It's just a constant number going in and a constant number coming out. And the question that we want to answer is, which direction does the thrust point? And so to start this, anytime you see something like a force, thrust is a force, or pressures, things like that, that's a clue that you need to conserve momentum. And so we start by writing out the momentum equation, d by dt, integral over the volume of velocity vector times rho d volume plus integral over the area of the velocity vector times rho velocity dotted with the normals dA, and that's going to equal the sum of the forces, remember, acting on the fluid. So let's look at our assumptions here. We can get rid of this term because it is steady. The forces are what we're looking for. And now it's just a matter of adapting this equation to our system. And so we need a few things. First off, we need a coordinate system. Let's call x that way, to the right. Let's define some normal vectors. Remember that they always point out. So normal vector at station 1 points to the left. Normal vector at station 2 points to the right. And so let's do a little bit of vector unpacking here. First off, velocity 1, v1, looks like the magnitude v1 times I. Remember, the normal vector is pointing to the left, so n1 looks like minus I. And that means that v1 dotted with n1 is equal to little v1I dotted with minus I, which is just minus v1's magnitude. At station 2, we have velocity vector 2 coming out, v2. It is in the I direction, positive. And our normal vector 2 points to the right, or the positive I direction, so that's into I. And then we can write that, v2 dotted with n2 is equal to v2I dotted with I, which is just equal to the magnitude v2. So we can sub these into our integrals. It feels a lot like doing a math problem. It's just we're going to get an extra thing, right? We need the velocity vector first. So the integral over a1, velocity at 1 looks like this. And so it's the whole thing, v1I. Now we need to multiply that by rho, and then by v dot n at station 1, which is minus v1 times dA. We're going to add to that integral over area 2. Again, we need the full vector, which looks like v2I. Going to multiply that by rho. Then we're going to multiply by v2 dot n2, which is just v2. Multiply all that by dA, and that's going to equal sum of forces. Now, I want to point out real quick, not that this is going to matter all that much, but this is a compressible flow problem. Jet engine's working on air, and so technically speaking, we need rho 1 and rho 2 because the density could change. All right, so let's work this out. These integrals, conveniently, since everything's uniform, we can pull things out, and so we're left with minus v1 times v1 times rho 1 times a1 times I hat. Over here, we can pull everything out, so we get v2 times v2 rho 2 A2 times I, and that's equal to the sum of the forces, which is what we're looking for. Now, you may or may not see this, so let me point it out. V1 times rho 1 times A1, well, that's just m dot 1. Over here, V2 rho 2 A2, well, that's m dot 2. Oftentimes, when you're working in a momentum problem, you're going to discover that you don't have everything you need until you apply a second law. One of the laws we could apply is the conservation of mass, which says m dot 1 plus m dot 2 has to equal 0. In other words, we've conserve mass. That's a second law. And what that tells us is that we can just rewrite those as m dots. Well, they're not equal to m dots, but we can call them m dot instead of m dot 1 and m dot 2 because they're the same value. And what that means we can do is we can write V2 minus V1 times m dot times I hat equals the sum of the forces. And so let's interpret this. The question was, which direction does the thrust point? Okay, well, we said that V2 was bigger than V1, so this whole thing is positive. V2 is bigger than V1, and therefore the force, the sum of forces here, is in the positive I direction. In other words, the force that we found from this equation, positive I, is to the right. But be careful. The force that comes out of this is the force on the fluid, So of course it's to the right. We said V2 is bigger than V1. How's that happen? Well, we pushed on it. So this is why it speeds up. Well, that's not what we're after. We're after the thrust, which is the force on the plane. And we can think now the force on the airplane itself is equal and opposite to the force on the fluid. And so the force on the plane is to the left, which makes sense because air goes in the front end of the engine and out the back end, and the airplane moves forward. And so force on plane goes to the left, force on fluid goes to the right.